Hi, I am Dilip Kumar Mangali and my teammate Hari Venkata Raviteja Anvakonda will be presenting our topic information extraction from images and videos. In simple terms, this field focuses on how machines can actually understand visual data, not just look at an image or a video but identify what's inside it, what actions are happening, and what relationship exists between objects. We call this process visual information retrieval, where AI systems can extract meaningful details from raw pixels and transform them into structured knowledge. Throughout this presentation, we'll explain how the technology works, why it's becoming so important in 2025, and the techniques that make it possible, from deep learning models to computer vision pipelines. Now, we'll begin with a short introduction explaining what information extraction actually means and how it applies to images and videos. Then we'll talk about why this field is becoming increasingly important, especially with the rise of AI-driven visual data. Next, we'll walk through the core pipeline, which shows how raw visual data is processed step by step into meaningful insights. And after that, we'll look at the key techniques for image and video information extraction, exploring the methods and the models used. We'll also highlight some real world applications where these technologies are being used today. Toward the end, we'll touch on evaluation metrics, current challenges, and finally discuss future trends and our conclusion. By the end of this representation, you will have a clear understanding of how machines extract and interpret information from visual data in our everyday world. Now let's begin with what visual information extraction actually means. In simple terms, it's a process where computers automatically identify and retrieve meaningful information from visual content like images or videos. You can think of it as teaching machines to truly understand what they're looking at. Not just pixels, but real world content like people, objects, actions, and the relationships between them. This field is important because most of the data we generate today is visual. Converting this raw, unstructured data into structured, searchable information allow us to apply it in the real world domains, from healthcare and security to self driving cars and online search. As shown in the diagram below, the process begins with raw visual data, moves to processing and analysis, and ends with extracted information that's ready to be used for decision making or retrieval tasks. In short, visual information extraction bridges the gap between what computers see and what humans understand, enabling AI systems to perceive the world more intelligently. In today's data driven world, visual information extraction has become extremely important. Every second, massive amounts of visual data from social media, surveillance cameras, and imaging are being generated. The challenge is that this data is mostly unstructured, meaning it's hard for computers to analyze or retrieve useful information without intelligent processing. This growing surge of visual big data is both a challenge and an opportunity. If we can successfully extract structured information from it, we unlock powerful insights, such as identifying diseases in scans, improving traffic systems, or enhancing content recommendations on digital platforms. The rise of deep learning has made this transformation possible. These models can now interpret complex images and videos, turning raw pixels into actionable intelligence. If you look at the chart below, you can see that visual data now represents the majority of all global data, far surpassing text, audio, or other forms. This clearly shows that the future of information retrieval depends on how well we can extract and understand visual information. Without these techniques, most of the data will remain untapped and wasted. Now that we understand why this field is important, let's look at how the process actually works. The core pipeline of visual information extraction. It follows a structured computer vision pipeline where raw data from images or videos is gradually transformed into meaningful insights through four main stages. Step 1 is input. So, this is where the raw visual data is collected from different sources like cameras, satellites, medical scanners, or online platforms. Step 2 is processing. Here, the data is cleaned, enhanced, and pre processed, for example, adjusting brightness, removing noise, or resizing images to make them ready for analysis. And step 3 is detection. This is the analytical core. At this stage, algorithms and deep learning models identify key patterns like objects, spaces, actions, or events within the data. And step 4 is the output. Finally, the extracted information is structured into usable insights like object labels, bounding boxes, captions, or summarizes that can be stored, searched, or interpreted. Each step is essential because together they enable machines to move from raw pixels to real understanding, making this pipeline the backbone of modern visual AI systems. Now, let's look at the major techniques used to attract information from images. The goal here is to convert raw pixel data into something meaningful that a computer can understand and describe. The first technique is detection. This helps the system locate and identify objects within an image. For example, detecting pedestrians and vehicles for autonomous driving or identifying tumors in medical scans. Common models used for this are YOLO, you only look once, at and RCNN region-based convolutional neural network, both of which can classify multiple objects in a single image. When it comes to videos, the extraction process becomes a bit more complex because you are not only analyzing images, but also dealing with the motion and time. The first technique is frame by frame analysis. Here, each video frame is treated like a single image and processed sequentially. This helps extract features such as color, motion, and objects, which form the base for higher level video analysis. Next is action recognition, where the system identifies what's happening in the video, like running, waving, or driving. Deep learning models such as 3D convolutional neural networks and LSTMs are widely used here because they can understand temporal patterns, meaning how actions evolve across multiple frames. Then we can scene change. Then we have the scene change detection. This automatically detects transitions between scenes. For example, when a new segment switches to a commercial or a movie changes location, it's an important step for video indexing and summarization, making it easier to search along with videos quickly. Lastly, object tracking that focuses on following specific objects across multiple frames, like tracking a ball in a sports video or a vehicle in a surveillance footage. Algorithms such as Kalman filter and short maintain each object's identify and estimate its movement trajectory accurately over time. The diagram below shows how this process flows. Starting from raw camera video, features are extracted, detections are made, and then tracked continuously through estimation models. Together, these techniques enable computers to not only recognize what's in a frame but also understand what's happening through time, which is a foundation of intelligent video analysis.
Thank you, Dilip. Let's start with how machines actually see and understand images. Object recognition and classification are core of visual information extraction. They help systems identify what's inside an image and where it is. For example, in picture, the AI detects a person, a car, a dog, even assigning a confidence score. This means the model isn't just saying there is a car, it's saying it's 99% sure this is a car in this exact location. This process bridges the gap between human vision machine perception, allowing computers to categorize and localize multiple objects like our eyes do, but with far more precision and speed. Once an image is recognized, the next step is feature detection and extraction. Think of this as teaching the computer to notice what makes one object different from another: the edges, the corners, and textures. In this highway image, the system detects multiple machines, vehicles using these extraction features. Each bounding box here represents an object identification through key points and patterns like construct and shape. These extracted features becomes the foundation for computer vision tasks such as tracking, recognition, and even 3D reconstruction, turning raw pixels into meaningful insights. Now that we understand the process, let's look at where technology actually impacts us. Visual AI is powering surveillance, systems that detect threats in real time, assisting self-driving cars in interpretation, road scenes, and even helping doctors read X-rays and MRIs with higher accuracy. It's also transforming retail, optimizing layouts, and tracking customer behavior, and making platforms like YouTube and smarter with automatic video summarization. Especially, visual AI has moved beyond labs. It automating everyday decision and shaping how industries operate. Of course, even intelligent systems needs a way to measure how it's performing. And that's where evaluation metrics comes in. Metrics like accuracy and F1 scores tells how reliable and detections are, while interception over union or IOU measures how closely and predicted objects box makes the real ones. In example, you can see overlap between the red and green boxes. That overlaps ratio is IOU. The higher it is, the better model perception. This matrix helps researchers fine-tune models to be more robust and trustworthy in real-world scenarios. Despite all this progress, visual information extraction still faces some major challenges. For example, models often struggle under poor lighting or when objects are partially hidden. Complex scenes like crowded streets make it harder to separate one object from another. Another big issue is cost of data labeling. Manually tagging thousands of video frames in both time consuming and expensive. And perhaps the most interesting challenge today is explainability. Understanding why an AI made a certain prediction, becoming a vital and safety trust. Ongoing research is focused on making these systems more interpretable, efficient, and adaptive in the real world. Looking ahead, the future of AI is incredibly promising. We are moving toward multimodal retrieval and text, while image and audio are analyzed through image searching and video using sentence. Generative AI is now helping summarize long videos automatically, perfect for platforms flooded with content. And real time with efficiency is becoming key. Models that can analyze visuals instantly for autonomous vehicles like monitoring and AR systems. In short, the future of visual information extraction is not just about seeking, it's about understanding, interpreting, and acting when it's seen, faster and smarter than even before. Thank you.